In this lesson, we're going to be continuing with our discussion of vectors, and we're going to be looking at the idea of scalar multiplication of a vector. Now, it's important to remember, why am I distinguishing here? Why am I saying scalar multiplication as opposed to just multiplication? When we first talked about vectors, we talked about the idea that a vector has both magnitude and direction, whereas a scalar only has magnitude. So when we talk about scalar multiplication of a vector, we're talking about a scalar quantity, no direction, just a number. So just any number that you're familiar with. And then a vector, which is this other type of construct that has both magnitude and direction. So if I start with a vector, so I'm just going to call that vector A. If I then write Ka, where you can see K doesn't have a vector symbol, so that would be a scalar multiplication. K represents the scale factor of K. And that's what I'm doing. I'm essentially taking my vector A and I am scaling it in some way. So I can actually show you this kind of happening in real time. It sounds much fancier than it's actually going to be. So if I start off with a vector, let's call that my vector A. So if I start off with the vector A, if my scale factor is bigger than 1, that means my original value for A is going to be stretched. So if I clone that so that we have a reference there, if my K value is greater than 1, then what I'm saying is it's essentially going to be stretched. And it could be stretched by a little, or it could be stretched by a lot. And that I've chosen to use terminology here that you should be completely familiar with when we've talked about in the past transformations of functions. Y equals a f of bracket k x minus p plus q, standard transformation of any function. We've talked about the a value in front. If the magnitude of a is greater than 1, we have a stretch, and in this case it would be a vertical stretch. If the magnitude is less than 1, we'd have a compression, etc. And then if the value is negative, we have a reflection. So that idea of stretch, compress, and reflect should be familiar to you already. So the same thing occurs down here. If my value of k, if the magnitude of k, if the absolute value of k is less than 1, that means I have a compression. And I can have a fairly minor compression, or I can have a fairly substantial compression. But I've made the magnitude of this less. Now the one thing I haven't done yet is I haven't talked about what if these values are negative but also bigger than 1, for example negative 5. Well, if I did negative 5, the negative part means I'm actually pointing in the opposite direction. Those are roughly the same length line, so you can see this is an example of just negative a. So if I did negative 5a, it might look more like that. It's 5 times longer than the original one, but it's also pointing in the opposite direction. So those are all examples of the idea of a scalar multiplication. Essentially what I'm doing is I'm taking some original vector and then I'm stretching it, I'm compressing it, I'm possibly reflecting it, and once I've reflected it, I may also be compressing or stretching it. I have all of those different possibilities available to me. So here's some illustrations and just the text that goes along with that. So these are the different effects that k can have on the vector A. We're going to start with k equal to 1, which essentially 1 times a is just a. So that's our original vector, which I've given some arbitrary length to. Now I've broken it down a little more specifically. So here I have k greater than 1. It's positive and greater than 1, so it's going to be a stretch. Here is k between 0 and 1. It's still positive, so it's still pointing in the same direction, but now it's a compression. This is interesting because we've got the 0 vector in this case. Just to remind you of the notation for that one, it's a 0 with a vector symbol above it. It is important, even though we're multiplying by 0, it is important to maintain the vector symbol here. It's still a vector, it's just a vector that doesn't have a vector, that doesn't have a direction that we can describe or define. And so the way we cover that is with this symbol, the zero vector. Here I have a compression. I'm dealing with a small number, but I'm dealing with a small negative number. So here's my original vector. I've flipped the direction of it, but I've also made it shorter. If k is -1, there's no scale effect, there's just the reflection. And if k is a negative number but a larger negative number, not only do we have the reflection, but we have some scaling going on, some stretching going on. Now when we talk about these vectors, all the vectors I just showed you except for the zero vector are considered to be collinear. And the reason why I excluded the zero vector is because when we talk about collinear vectors, we're talking about parallel vectors. So they can be arranged to lie on the same straight line. The zero vector has that kind of strange property that its direction itself is not defined, and so we can't say that it's collinear to any of these. You could, I guess, argue that it's collinear to all of these, or that the zero vector is collinear to all other vectors. That's something I think I'll have to look up and clarify as we talk about it in class. Because looking at this definition makes me suspect that the zero vector actually falls into that collinear category because it's k member of R, and so that would include k equal to 0. But it didn't include the zero vector here, so like I say, we'll clarify that later. So again, I've started with my original vector A, and so what are some examples of collinear vectors? Well, basically anything that's parallel to A, whether it's parallel and in the same direction or in the opposite direction. It's also important to note that collinear doesn't mean that they're on the same line, although you would think that collinear, doesn't that mean collinear, same line? They share a line. But this point is important, is that they can be arranged to lie on the same straight line. Because with vectors, although we define vectors quite often in terms of their starting and ending point, we can then pick up a vector and we can move it around when we're talking about it. And so that's what we mean by arranging vectors so that they are collinear. Because I can arrange these vectors so that they're all collinear. Because when I do try to put them on the same line, they all end up along that exact same line. Now, vectors have magnitude and direction, and we've talked about that before, and we'll talk about it again. There are different ways to express this idea of magnitude. Well, not magnitude. Magnitude is a number, but how we express direction can vary depending on the situation or the application that we're trying to fulfill. So in this case, vectors x, hopefully you can forgive me for not putting the symbols there. It's sometimes inconvenient to do that. That's why I use the word vectors. So I'm describing that this is the vector x and this is the vector y. And in particular, they are unit vectors. So we're going to talk a little bit more about a unit vector coming up. But a unit vector, what that means is that it has a magnitude of 1. So the magnitude of each of these, the length of each of these is 1. And it says they make an angle of 30 degrees between them. And I believe you've done something in your homework that looks somewhat similar to this. So what I'm going to do is I'm going to draw these out. Usually it's a good idea, just pick one to be in a reference direction. Often that's just going to be your y-axis or your x-axis. And 30 degrees is there. It doesn't matter how long I draw these, but I do have to remember that each of these has a length of 1. They're unit vectors. And we're told that there's an angle of 30 degrees between them. But what I want to do is actually determine 2x minus y. So I'm going to call this one x, and I'm going to call this one y. That part doesn't actually matter. All that matters is that I stay consistent once I've made this choice. So in doing this, so 2x, I've got 2x minus y. So it might be worth pointing out. So 2x, well, that's just doubling x in that direction. So that's okay. I can just go ahead and say that's 2x. Now minus y, and I think I'll do this by hand, if this is my y vector, then the negative y vector has to be in the opposite direction. So 2x minus y is actually the same thing as 2x plus the negative y vector. And that's helpful because that's where I'm going to draw in my second vector, and that's going to go here. So there is my negative y vector. But the important thing to remember, these were unit vectors, so I know that this is actually a length of 2, and I know that this is actually a length of 1. Now what about that angle in between? If we go back to our diagram here, you can see the angle I'm looking for is here, which is this angle, but because these are two straight lines, that's also equal to 30 degrees. So that is the angle 30 degrees. So the first thing we want to do is we want to figure out magnitude. So we want to find out how long is this side. And the way we're going to do that is using the cosine law. So for the sake of argument, well, you know what, I'm just going to go ahead and I'm going to write it out using vector notation. So it starts here. I'm going to kind of cover up that one arrow on the end. And I'm going to make this other arrow a little bit more pronounced. So when we say 2x minus y, it's here is my starting point, and here is my end point, and how I get from that start to that end is the vector 2x minus y. So what I want to do is I want to find the magnitude of 2x minus y. That's the first thing I need to do. And the way I'm going to do that is using the cosine law. Now the cosine law it's a little bit more than this, and I'm just going to remind you of what the cosine law, how it's written. It says that a squared is equal to b squared plus c squared minus 2bc cosine of the angle A. So in terms of what we have the magnitude of 2x minus y all squared equals the magnitude of b, so that's just one of my other two sides, which I have one side that's 2, so I'm going to square that, plus another side that's 1, and I'm going to square that. 2 times 2 times 1 times the cosine of the angle between them, which is 30 degrees. And so I get the magnitude of 2x minus y is equal to, now I could stay with this, you know what, I think I will. I'll stay with this being squared, and we end up with 4 plus 1, and I've got minus 4, and now I need the cosine of 30, and I always like to just remind you, just in case, of your special triangles. And normally we've been doing this in radians, but hopefully we can remember how to do this in degrees as well. And so we want the cosine of 30 degrees, which is root 3 over 2. So this is going to be 4 times root 3 over 2. And then from there, we're going to simplify. So the magnitude of 2x minus y. This can get a bit unwieldy. If you want to let a variable stand for that, if you want to say, I'm going to let L represent the magnitude of this, there's nothing wrong with that. And that's just a convenience decision. Just make sure you communicate that that's what you're doing. So we end up with 5, and then 4 divides into 2, goes into 4 twice and goes into 2 once. So we get 5 minus 2 root 3. And now it's probably a good idea, we can go ahead and take our square root of both sides. And normally we take the square root of both sides here, we would say plus or minus, but we don't need to do that because we know this is a length, this is a magnitude. And so we know that L must be greater than 0. We know a length has to be greater than 0. And so from that, we end up with, now we can write it this way. This is an exact value, and this is perfectly good this way. And you might also, depending on the situation, you might also write that as an approximate value, which is 1.24. Now that's the first part. The next thing we need to do is actually look at how do we describe this? How do we describe this vector 2x minus y? Because so we have an existing vector x, we have this vector y or negative y. So generally what you're going to want to do is you're going to want to express this in terms of, well, the starting point was based on x. So what I'm going to do is I want to figure out this angle theta so that I can express my vector in terms of that angle theta. And so if we take a look at it, what do we have here? What can we make use of? So um, if you remember some of your obtuse or non-right triangle laws, sine law and cosine law, here we're looking for this angle. We have this side, so we have side, angle, side. And so that would allow us to find this opposite side, but we already know that. We also have angle, side, side. That's the impolite way of saying it, or side, side, angle. But when we do side, side, angle, we do have to be careful because when you do side, side, angle using sine law, you might be dealing with the ambiguous case of the sine law. Do we have any other options though? Is there anything else that lends itself here? And it doesn't actually look like there's anything else I can do with this. So I'm going to use the sine law. I think I'm actually going to take just a quick copy of this. Bring that down here and I will paste it. Okay, and so now I'm going to go ahead and construct my sine law equation. So I'm interested in theta, so I write sine of theta over, and the side that's opposite to theta is 1, so that works out nicely, is equal to, now the only other place I have an angle is the 30 degrees, and that's a little inconvenient because the only thing that's across from that is the one we just figured out. It's, if possible, we don't want to use the value we just calculated as our starting point for our next calculation, but of course that's not always an option. So we end up with the sine of theta is equal to, and I just cross multiply that 1 up there. So I end up with the sine of 30, which we can get from our special triangle again. Sine of 30, thankfully, is nice and easy. That's just a half. So that's 1 over 2. All divided by the length of this, which is the square root of 5 minus 2 root 3, and that's not particularly nice. And then from that, we end up with theta is equal to, now we have to consider both our ambiguous cases here. We don't want to be sloppy about this. And so what that really means is that my related acute angle is equal to, if I take the sine inverse of this whole thing, I end up with 23.8 degrees. And we've got this being positive, cast rule, and this is why it's the ambiguous case, because it could be positive in quadrant 1 or quadrant 2. But if you think about that for a second, if it's in quadrant 2, then it would be 180 minus this, which is actually 156.2 degrees. But I know that I already have a 30-degree angle in there. And so 156.2 plus 30 is more than 180 degrees. So my quadrant 2 answer is inadmissible, because that would give me an angle or a triangle more than 180 degrees. So actually I end up with theta is equal to 23.8 degrees. So now that I've done that, I have to describe it. And this is really the important thing that I wanted to get to here, which is therefore my description of 2x minus y is equal to, and the way I'm going to describe that is I'm going to use my approximate, so 1.24. So that's approximately equal to 1.24. And then quite often with vectors, we'll represent them. You can represent them as a statement in English, but we can also represent them using these square brackets. That's a convention from physics, which we're going to be using here in math as well. So how can I describe this? This is the angle 23.8 degrees, and the angle is this way, which is clockwise. So we say 23.8 degrees clockwise to the vector x. It's still kind of awkward, but it does the trick. Okay, and I think this is our last bit, or certainly our last example here. An airplane flies north 30 degrees east at an airspeed of 240 kilometers per hour. Represent this using vector notation. So what I want to do is, again, same idea. So I'm going to say the velocity of this plane, that's vector notation, is equal to 240 kilometers per hour. So a scalar with the units, and the direction is north 30 degrees east. You will sometimes see this written this way: 30 degrees east of north. Those are equivalent to each other. Sketch this situation. So to sketch this situation, what I'm going to do is I'm going to just put on north, east, south, and west. And the airplane flies north. So we start north and then we turn 30 degrees. So we start north and then we turn 30 degrees towards the east. And then that gives us our vector. And however long we choose to make that, that's up to us. That's simply, so there is our vector, which is 240 kilometers per hour. Now, I don't have to put a direction here, even though it's a vector, because the direction is taken care of by the actual diagram. And then part C says the return flight occurs at 150% of the original speed. So 150% of the original speed means it's a scale factor of 1.5, but it would be in the opposite direction. So that's going to be negative 1.5. So if we call this one V1, then V2 is going to be equal to negative 1.5 V1, which is negative 1.5 times 240 north 30 degrees east. And notice that I have not put in the units this time. And that's equal to negative 360 north 30 degrees east. But we're rarely interested in representing a vector this way. Much more useful to us is to represent this as a positive. But to do that, I think it might help for you to see, and I'm going to take that line that we had, I'm going to extend it. So if this is 30 degrees, that means this must also be 30 degrees. And the reason why I'm doing that is if this is in the opposite direction, it means it's still on that line. It's collinear. I didn't want to do that in the same color. It's in the opposite direction, but it's collinear, but it's longer. So this one is 360 kilometers per hour. And so what is that direction? Let's write this now as a positive vector. And notice this is just an equal sign. I'm continuing this. That is equal to 360. And instead of it being north 30 east, it's now in the opposite direction, which is south 30 degrees west. And I think that's it, because then it asked for the diagram to go along with that. So you do need to be comfortable with your just plain geometry, that sort of thing, in order to be able to express these things well. And last thing to talk about, no example to go along with this one, is this idea of a unit vector. A unit vector is something that's really very useful. I know from experience in physics, we use unit vectors all the time. Other areas of mathematics, fields like engineering, any field that makes use of vectors will often be interested in unit vectors, and that's because having a length of 1 is very convenient. If we need to create a unit vector, we start with any original vector, and we create a new vector where we take the original vector and we divide by the magnitude of the original vector. So for example, if I had a vector v, which was 5 north, then I could make a unit vector which is equal to v over the magnitude of v. And in this case, the vector v would be 5 north. The magnitude of v, how big is v after we ignore the direction? Well, that's just 5. And of course, those divide out and those divide out. And we end up with our unit vector is just equal to 1 north. And that's just one example of how you might do that. Okay, that's it. I feel like this one went a little bit long. Probably my fault for talking too much. There's your assigned work to go along with these concepts.